Welcome to this week's second lecture in EE404. In the last lecture, we have completed the results on the existence and the non-existence of limit cycles or periodic trajectories. In this lecture, we are going to start another method that is used for dealing with oscillations. The difference of the current method with the earlier ones would be that the current method is an approximate method. The new method is called describing function analysis, and it is used to predict the existence or the non-existence of limit cycles, as well as, and with this method we can actually find also the parameters, approximate parameters of the periodic trajectories, like their amplitude or their frequency, etc. So let us start with today's topic, describing function analysis. So I will first write some facts about this method, and then we are going to try to see what this method is all about. So first of all, this is an approximate method, which means that its results might not hold in reality. So we can find we can predict the existence of a limit cycle or existence of a periodic trajectory, and this result might not hold in reality. Or we can actually we can correctly find the existence of a limit cycle, and we can try to predict the frequency and the amplitude of that limit cycle, and the results we would find would only be approximate ones, all right, in reality. So this is an approximate method. This is contrary to the earlier results, which were exact theorems actually. So let us write what we can use for this method for. Well, we can determine the existence or non-existence of a limit cycle or periodic trajectory. This is one of the uses of this method. The second thing is that we can determine the approximate frequency of oscillations and their amplitudes. Okay? And finally, the third thing that we can determine with this method is the stability of the oscillations. We can determine the stability of the oscillations. Of course, if they exist. Okay? So the describing function method is an approximate method, and we can determine the existence, non-existence of a limit cycle periodic trajectory with the describing function analysis, and we can determine the approximate frequency of oscillations and their approximate amplitude, and we can determine the stability of the oscillations, so if the oscillations are stable or not. So if we find a limit cycle, is that limit cycle stable or an unstable limit cycle, we can determine those type of properties of the oscillations. This method always uses the following type of block diagram. So we need to have a system in this form in order to be able to apply the describing function analysis. So we need to have a feedback loop in this form. Okay? Of course, I can have other linear blocks here. It really doesn't matter. Okay? So I can have h of s here. So this method would always use this type of block diagram. It can be applied only to this type of block diagrams. And here we have these two. They are linear systems. Okay? And there is a nonlinearity here. Okay? This is nonlinearity. So here, we again in the overall, we have a nonlinear system because this system is not composed of all linear systems. If it was composed of only linear systems, then the overall system would be actually linear. Okay? But here, because of this nonlinearity here inside this block, the overall system becomes a nonlinear system. Okay? So here, the linear system here, G of S, so here I already told you that there can be a feedback loop here, like this. So that in the feedback path, I don't really have to have the unity feedback. So I can have an H of S here, which is a linear system as well. But here I will assume for the simplicity, I will assume that this is unity feedback, okay? But you can always put here another system, another linear system that would represent your sensor, right? But now for the time being, let us assume that we have a unity feedback system, and I have the only linear system here is given by this. So here, the linear system, G of S, is assumed to be low pass. Okay? What do we mean by that? If you look at the amplitude of G of j omega, okay? If you look at this amplitude, I have omega frequency here, we need to have a decay for high frequencies, okay? So either the G of j omega should be in this form, it is attenuating higher frequencies, that is a low pass type of filtering structure, or it needs to be like this, okay? It is both of these type of systems are called low pass systems because they are punishing high frequencies, all right? So here I will give you some example nonlinearities that we can use with this method. So let us write some example nonlinear elements. Well, what we mean by nonlinear element is nothing but that function f. Okay? So the first element that we can consider, the first type of element we can consider might be just a switch, okay? So we have a switch given like this. I have here A and minus A like this. So I have here the input of the nonlinearity is X and the output, let us say, is Y. So this is a switching type of nonlinearity, and in nonlinear control we would call this type of elements as a relay. Okay? A relay type of nonlinearity. It's just a basic switch. All right? The second type of nonlinearity that we can, these are just some types of nonlinearities that we can consider. Of course, the method is not constrained to these types. We can consider any type of nonlinearity. These are just some examples. The second type is called the so-called saturation type of elements. Okay? And we have this type of figure for that. I have XY. So you see here that actually this element is linear in some range, and then we have some saturation. When the magnitude of the input becomes larger than a threshold, then the element saturates. This is actually a physical phenomenon seen in actual systems. So suppose that this F represents an actuator in your control system. By an actuator, I would mean an electric motor, for example, that might apply a torque input to the system that you would like to control here. In that case, so electric motors can always have a maximum torque allowed with them. Okay, so the electric motor might not supply any torque, arbitrarily large torque that you might want. Okay, there is always a limit that can be on the torque that can be supplied by an electric motor. So if you ask for a larger torque than the maximum torque that can be supplied by the electric motor, it's going to supply the maximum torque to you. Okay? In that case, this type of saturation elements would make sense. Okay? So it is so your physical system, your actuator has some limits, and it cannot supply some torque with a magnitude larger than a threshold. Then you can put this in your mathematical model to model those saturation effects in a better way. The third type of nonlinearity, example nonlinearity that we can consider might be, so this is saturation. The third type is called a dead zone. Okay? So this is called a dead zone type of nonlinearity. And in this case, you see that the nonlinear element gives you just 0 in some range for small values of the input, and it gives you non-zero results when the input gets outside that range. This is also a physical phenomenon that might be observed in real physical systems. So if you take a DC motor, for example, if you apply a small voltage to its terminal, voltage epsilon, for example, you will see that for small voltage values, the DC motor will not actually turn at all. So it's going to supply you 0 velocity initially for some small voltage values. All right? The motor will not, if I increase the voltage from 0 to epsilon, the motor will not start moving immediately. Okay? So it is not a linear profile that you are going to see. For some small voltage values, the velocity of the electric motor will be 0, and only after you increase the voltage above some threshold that will you be able to see a non-zero velocity from that in that DC motor. Okay? So this type of nonlinearity is called a dead zone type of nonlinearity. Okay? So all of these three types of nonlinear elements, they are called static nonlinearities. So these were static nonlinearities. So relay, saturation, these are examples of static nonlinearities. Dead zone. What do we mean by static? Static means memoryless. Memoryless. Okay? Without a memory. What does it mean? It means that when you apply a single x value, single input to these nonlinearities, you would always get the same output. Okay? So for a single x value, we have a single output value for these nonlinearities, for the saturation as well, and for the dead zone as well. There are also other type of nonlinearities that we can consider with the describing function analysis, and these are called the dynamic nonlinearities. Dynamic nonlinearities. And these are nonlinearities with memory. Okay? What can be examples of this type of nonlinearities? The first type is going to be, again, a relay type of nonlinearity, but it's going to have a hysteresis in it. Okay? So we are going to have a nonlinearity in this form. All right? So here there are some arrows to show what type of behavior this nonlinearity would have. Okay? So you see that when you look at these characteristics of this nonlinearity, it has a hysteresis in it. So for some values of x, the nonlinear element value is fixed. Okay, let us say that these are minus a, this is a, b, and minus b. For some values of x, there is a fixed nonlinear element output. But for some other values, I would have double value of the nonlinearity. And which of these values would be valid is determined if x is increasing or decreasing. Okay? If the value of x is increasing, then the below value would be valid. If the value of x is decreasing, the value above would be valid. So in some way, in this nonlinearity, not only x is important, the value of x is important, but we need to also know the derivative of x, whether it's positive or negative, to be able to determine the value of the nonlinearity in this range. When x is between minus a and a, I need to know, in addition to x, I need to know the derivative of x, which is a form of memory. Remember, derivative, you can calculate a derivative or some slope only if you know more than one value of the function. So knowing the derivative requires a form of memory. All right? So that is why this element is called a dynamic nonlinearity, which means a nonlinearity with memory. So I need to know not only x, but also it is derivative as well, in order to be able to determine the value of the nonlinearity between this, when x is between this range minus a and plus a. Okay? So here, what type of element this hysteresis might represent? Okay. So I will try to show you an example. Suppose that I would like to, let me say example, control the room temperature with an air conditioner. Okay. Suppose that I would like to set the temperature of a room to a constant. Let us say that the reference is 27 degrees. All right, degrees Celsius. All right. So here I have a control system, and suppose that I put here just a simple relay, simple switch. Okay. This simple switch is modeling the air conditioner behavior, okay? And I apply the output of the air conditioner to the room model here, okay? This is modeling the air in the room that is given by transfer function g of s, and this variable y is the room temperature, okay? And currently, I have only a relay here, a simple switch. What does that mean? This means that I have the error signal here, and I have the input signal u here to the system. Okay. So here I see that u of t is nothing but a times sine of e. Okay. in this case, I would have this type of nonlinearity here in the system. So now let me assume that currently the room is at 24 degrees. Okay? So let us say that y of 0 is 24 degrees Celsius. All right? What type of behavior is this control system going to give to us? So if I draw the output of the system, t, with respect to t, then the behavior is going to be like this. This is my reference, 27 degrees Celsius, and currently we are at 24 degrees. Okay? So currently, I have 27 minus 24. The error signal is positive. Okay? And since the error signal is positive, the air conditioner is going to apply heating. So plus A here represents heating with some intensity, and minus A represents cooling with some intensity. Okay? So in this case, I would apply heating onto on the room. Okay? So the temperature is going to start increasing, and the error is going to get smaller and smaller. Okay? Then we are going to hit the 27 degrees. All right? The actual room temperature is going to hit 27 degrees, but since I will not be able to sense this immediately, it is just going to go slightly above the 27 degrees, 27.0001 degrees. Okay? As soon as we pass that value, the controller is going to switch to the second regime. Okay? In that case, it's going to start cooling. So the room temperature is going to start getting smaller and smaller. And just below 27 degrees, we are going to switch again. And then just above the 27 degrees, we are going to switch again to cooling, heating, cooling, heating, etc. Okay? So in this manner, we are going to have a very high rate of switching in the controlling. Okay? So we are going to start air conditioning, start heating, then start cooling, then start heating, start cooling with a very high frequency. This type of behavior is called chattering in control. Okay? So we really would like to avoid this type of behavior of the controller, because switching means that we are playing with some physical elements, and if we need to switch quite frequently, then that element is going to get older and older. So it is not going to be useful anymore after some time. It's going to get old quite soon. All right? So that means that we need to avoid that type of chattering, and that is where this type of relays with hysteresis might be useful. Relay with hysteresis. Okay? And what does it do? So let me say that instead of this perfect relay here, let us say that I put here a relay with hysteresis. Okay? In that case, it will be just like this. So it's going to be similar to a relay, but it's going to have a hysteresis in the middle. Okay? Let us say that this point is -2 and this point is +2. So these are the limits of the hysteresis behavior. So A is just 2 here, all right? So here I have +A intensity and -A intensities here. So the same intensities, but I would have -2 +2 limits hysteresis, okay? So now let me try to show you the behavior with the hysteresis. So this is relay with hysteresis. In that case, I would start here again exactly at the same value. But what is going to happen is that, so in this case, what is the error? 27 minus 24, error is 3. So we are outside the hysteresis region, so we are going to start heating. Okay? So we are going to have plus a value, which means start heating. So we're going to start heating here. And then on this error curve, so on this error is going to start decreasing and decreasing. But we are not going to switch at the value 2 here, because error is decreasing, the above value would be valid. All right? So when this temperature is increasing, error is getting smaller and smaller. All right? That means that the error signal is decreasing, which means that we need to choose this branch if we are somewhere here, because error is decreasing. So we're going to hit the value 27 here, but here the error is going to be 0, but still I would continue heating. Okay, because we are still at plus A. So this value is going to start increasing above the 27 degrees, and we are going to reach here where the error has to be minus 2. So when error is minus 2, we are going to hit 29 degrees. All right? So we're going to hit this value, and only then the controller is going to switch into cooling. All right? So we're going to switch into cooling. All right? Then as soon as we switch cooling, we're going to start going towards 27 degrees again. All right? And the error is minus 2 here, and it is going towards 0 again. So the error is increasing. So from here, we came here and we switched, and then the error starts to increase again. But because error is increasing, we are going to choose the lower branch here. All right? Not this branch anymore. So the switching is going to take place when error is plus 2 this time. So we're going to pass through 27 again, and we're going to go into 25 degrees. All right? And then we're going to switch at 25 degrees. Okay? So we're going to be switching between 25 and 29 degrees like this. So you see that in this case, we are still switching. There is still some form of oscillation here, but our switching frequency is quite reduced here. Okay? So then our switch might have a longer life than the earlier case. So sometimes this type of hysteresis might be some artificial system, like this, the human-made system here. And sometimes hysteresis might be a physical property of the actual system. In DC motors, for example, you might see a hysteresis in DC motors or AC motors, I am not sure. In electric motors, you might see hysteresis behavior as part of the physical properties of the system. Okay? So this was the first type of dynamic nonlinearity, and the difference between the dynamic nonlinearities is that static nonlinearities, they would, for a single x value, they would always have a single y value. But here, you see that for some x values, we might have different y values, more than one y values, and which one of those y values would be selected would be determined by the history, which means that we need to have a memory in order to be, so this element needs to needs to have a memory in order to be able to work properly. Okay? So let me look at a second type of nonlinearity that is called a backlash. Okay? Backlash type of nonlinearity would have this type of behavior. I have x and y. So let me say that this backlash type of nonlinearity would work like this. and I will start here. So it would have a characteristics that would be given like this. And I would have here this type of, let us say, behavior. So now let me try to explain what backlash type of nonlinearity would model. All right? So sometimes we place nonlinear elements ourselves into our system. Okay? Like this relay with hysteresis example, to avoid frequent switching. Okay? Sometimes these nonlinearities are artificial elements that we place into our systems for better performance. But sometimes they are there because the physical system actually contains it. Like, for example, the saturation element. We really do not want that saturation in the system. We would really like our motor to give us any torque that we would like. But the physical limitations of the electric motor is actually giving us that type of behavior. That is in the physics of the problem, and we are placing the nonlinearities there because of those physical restrictions to be able to model the real system in a better way. Okay, so there are two types of nonlinearities: artificial ones and the physical ones. In the artificial ones, we are putting them into our systems ourselves. In the physical ones, we are putting them into our mathematical models in order to be able to model the physical reality in a better way. Okay. So now let me try to explain. So this backlash is usually not an artificial nonlinearity. It is an actually physical nonlinearity that is caused by the gear systems. So let me say that I have two gears like this. Okay. So these are dişli in Turkish, and I would have two gears here. All right. I'm actually drawing an exaggerated figure here. Okay. So these are continuing like this. These are circles, and these are just the tip of them when they are connected to each other. All right. So if I call the angle of the first gear as θ1, then I can call the angle of the second gear as θ2. Okay. So let me say that x is θ1 and y is θ2. Okay. So then when two gears are connected like this, these tooth here, they are called cogs in English. So I don't know what they are called in dişlilerin dişi. So I don't know what they are called in Turkish, but they are called cog in English. So of course the gears are turning because these cogs are touching each other, and then they are pushing each other in different directions. Okay, but you see that there is some kind of dead zone between these two cogs here. Okay, so when I turn the gear with angle θ1 here, okay, suppose that we are here. So when I turn this first gear a little bit, I see that these two cogs are not going to touch each other immediately. Okay? So θ2 is not going to immediately increase from its value. It's going to remain constant for some time when I increase θ1. Okay? So this θ2 is going to remain constant until these two cogs touch each other. Okay? So when I turn θ1 for some time, for some θ1 values, this θ2 is going to remain constant where it is. All right? And only after θ2, only after this cog touches this cog, we are going to have a motion in θ2. Okay? Let me say that this motion is like this. As theta 1 increases, as long as these two cogs are touching each other, we're going to have an increase in theta 2. Okay? So when I turn this is going to start moving after after these two cogs touch each other. This touching point is here. Okay? This is what theta 1 should be when these two cogs start touching each other. Okay? And after they start touching, increasing theta 1 is going to increase theta 2, like this. Okay? So suppose that after some turning, we turn the first gear back. Okay? After turning the first gear just a little bit in counterclockwise direction, suppose that I start turning it in the clockwise direction. Okay? In that case, these two cogs start from the touching position, but as soon as I start turning this first gear in the clockwise direction, they're going to be separated. Okay? And theta 2 is going to stop turning. Okay? So we started from here, and then we came here, and then now we are turning now we are reversing theta 1 in the other direction, and then this gear stops turning because the cogs are separated again. Okay? When I start turning this clockwise, the second gear is going to stop turning. So it's going to remain constant for some values of theta 1, and then only when this cog reaches to this cog that we're going to start having a decrease in theta 2. Okay? So it is this type of spaces between the cogs of the gears that would cause a backlash type of nonlinear behavior. Of course, usually this behavior is constrained to very small angles, okay? Because we don't really have gear cogs separated like this in reality. They are separated, but they are separated with a very small distance between them. All right? So that is still a behavior that might cause oscillations in nonlinear systems, okay? And we can use backlash model if we have gears that would work like this to model that type of behavior in our mathematical system. All right? So this is also, of course, a dynamic nonlinearity, because you see that for some theta 1 values, for some x values, it might take two different values. Okay? So this is also a dynamic element that is with memory. All right? So now we are actually ready with how this describing function analysis is made. I will illustrate describing function analysis method on a simple example, and I will give the fundamentals of the describing function method with theoretical details in the later parts of these lectures. So in this lecture, I will only consider a basic example to illustrate how this method would actually work. So let us say, for example. So this example is called Van der Pol Oscillator. And this so-called Van der Pol oscillator has the following second-order nonlinear differential equation. X double dot plus mu x squared minus 1 x dot plus x is equal to 0. Okay? So we have a second-order nonlinear system, nonlinear differential equation. And here, mu is a parameter which is positive. All right? And here what we need to do is to find the amplitude and the frequency of the oscillations of x. What is the amplitude and frequency of the oscillations. Of x. Okay? And we are going to use describing function analysis method for finding these quantities approximately. All right? The first thing that I'm going to, sorry, this is wrong. The first thing that I'm going to do is to explain to you why this system actually oscillates. So this looks like a second order differential equation, but why really it oscillates here? So let me first try to show you a linear system with a similar differential equation. I have m, and I don't apply any force here. So let us say F equals to 0 here. And this is x displacement. And suppose that I have a spring with spring coefficient k, and suppose that I have friction with friction coefficient b here. Okay? I'm sure you can actually extract the mathematical model of this thing. It is m times x double dot is equal to f minus bx dot minus kx. Okay? And if I collect all of the x-related terms on one side, I will get m times x double dot plus b times x dot plus kx. And here I know that f is equal to 0. This is equal to 0. Okay? So we see that this type of system would have, with 0 force, it would only work with the effect of the initial conditions. It will only have non-zero axis if we started with some non-zero initial conditions, and it would have this type of mathematical model. Okay? And here, m is constant, m is a positive constant, b is a positive constant, and k is a positive constant. Now go back to the van der Pol oscillator equation. It really looks like this type of equation as well. Instead, here, in the van der Pol oscillator, m is equal to 1, k is equal to 1, okay? And the coefficient of x dot, in this case, depends on x, okay? So b is equal to m x squared minus 1. Okay? So in that, the van der Pol oscillator is nothing but mass friction spring system where this friction depends on the x position of the mass. Okay? The displacement of the mass from the equilibrium. So we see that if the friction coefficient depends on the position displacement of the mass from the equilibrium, then we would get the van der Pol oscillator. So now suppose that the x value is around 0. Okay? Suppose that the x displacement is equal to 0. If the displacement x is equal to 0, I see that here this b becomes minus mu. If x is approximately equal to 0, then b becomes minus mu. And mu is positive. So I see here that we would have a negative friction coefficient when x is close to the equilibrium. Okay? When x is close to the equilibrium, we would have a negative friction coefficient. What does it mean to have a negative friction coefficient? So a positive friction coefficient, which we are more used to, means that the system is going to lose energy. Okay? Then a negative friction coefficient would be meaning that the system is going to gain energy when x is close to the equilibrium. Okay? So when x is close to equilibrium, the system is going to gain energy. But when that system gains energy, it means that it's going to start oscillating. It means that this x is going to start getting larger when that, or x is going to start getting smaller. All right? Spring can store energy in two ways. Either x starts to become small, or x starts to become larger than the equilibrium. All right? But when x is close to 0, the system is going to get some energy, so it's either going to, so the spring is going to have to either be squeezed or expanded. All right? What happens when x is very large? The magnitude of x is very large. In that case, the friction coefficient starts to become positive, meaning that system is going to start losing energy if x is very large. Okay? So we see that if x is close to 0, the system is going to gain energy, and x is going to start to get large in magnitude. And when x becomes too large, the system is going to start losing energy with positive friction coefficient. And therefore, we can intuitively say that the system is going to move back and forth between these two scenarios. Okay? So that is why this Pol oscillator would actually oscillate. And here what we have to do is to find the amplitude and or approximate amplitude and the approximate frequency of those oscillations. Okay? And for that, we are going to apply the so-called describing function analysis. But you see here that I've told you that describing function analysis would always use a block diagram of this form. But now we are given only the differential equation like this. So somehow, I need to find a way to convert this differential equation into this type of block diagram. Okay? So what I'm going to do here is that I'm going to try to make this output variable x, all right? And then I'm going to try to find this f and g of s for this equation to hold. Okay? So the first thing that I'm going to do is that I'm going to separate that differential equation into its linear and nonlinear parts. We see that in this block diagram, linear and nonlinear parts are separated from each other. That is what I'm going to do on the differential equation now. So x double dot plus mu x square x dot minus mu x dot plus x is equal to 0. So now let me collect all of the linear terms on the left-hand side and nonlinear terms on the right-hand side. Okay? So x double dot is a linear term, and then this term is definitely nonlinear because of the square and the multiplication of x and x dot here. It is nonlinear. So I will take this term on the left-hand side, mu x dot plus x is equal to, I would take the nonlinearity to the other side, minus mu x square x dot. So now I will just take this mu to the other side as well, because it's just a scalar multiplication. It's also a linear operator. I can actually, linear operation, I will also take it to the other side. So x double dot minus mu x dot plus x divided by mu is equal to minus x square x dot. Okay? So this is a fundamental equation that I can use to be able to actually form that type of block diagram. So here is what I'm going to do. So suppose that this output variable is just x. Okay? I will assume that the reference is 0 here. Okay? Then you see that this x signal comes here and it becomes minus x here. All right? So I will want f to convert this minus x into this nonlinear part. Okay? So I will want on the right hand side to have the signal minus x square x dot. Okay? I know that this is equal to this one as well. X double dot minus mu x dot plus x divided by mu. Okay? But I will want this f, I will find that f, such that when I input minus x into that f, I would get the output minus x square x dot. Okay? So suppose that I choose the input of f as the signal E, because this is the error signal. So I have E is equal to minus x here. And suppose that I would call the output of f as U. So this is my U here. All right? So here what I want is, I want to find a nonlinearity which gives me x square minus x square x dot when I give to it the input minus x. Okay? So I need to find U is equal to f of E question mark. Okay? What is that f of E in this case? So here I can actually write f of E as E squared times E dot. Okay? So this is my nonlinearity. It really doesn't have to be a static nonlinearity. It can contain derivatives, which are dynamic operators. All right? So here, if I select f of E like this, suppose that E is equal to minus x. In that case, I would have U is equal to minus x squared minus x dot. Okay? And this becomes x squared x dot, and there is a minus sign here, minus x squared x dot. Okay? So this is my f of E. This is my nonlinearity in my system. And what about G of S? I need to find a linear system such that this U signal, which is given either by this or this, and it has to convert this U signal into X. Okay? So you see that in the input of G of S, I have the signal U. U is equal to minus x squared x dot. I really do not want to use this one. I know that this is equal to this linear term. Okay? So x double dot minus mu x dot plus x over mu. This G has to convert this signal into X. It needs to take this signal as input and it needs to convert this into X. So what should be my G of S? That is our question. So this question might look strange to you, but when I try to look at some basic cases, you would understand what we would need. Suppose that this is x dot, and suppose that you would like to obtain x. What linear system converts x dot into x? Okay? X dot is the derivative of x. And you need, in order to be able to find x, you need to integrate. Okay? So here I would have 1 over s, the integrator system, would convert x dot into x. Okay? But x dot is nothing but s times capital X. And this is, so in Laplace domain, this is capital X. In Laplace domain, this is s times x. So that means that I need 1 over s to convert x dot to x. Okay? So now let me look at another basic example, x dot plus 2x. In order to be able to convert this into x, which linear system I would need to put here? Which linear system I would need to put here to convert x dot plus 2x into x? In Laplace domain, this is sx plus 2x, okay? But this is s plus 2x, and this is capital X, which means that I need to put s plus 2 here. Okay? So then tell me, this G of s, which would convert this signal into this one. So we see that here, in the denominator, I need to have s squared minus mu s plus 1, okay? Just similar to this one, okay? And in the numerator, I need to have mu. All right? So now we have obtained all components. So let me try to draw the block diagram here. The reference signal is equal to 0. And I would have the error signal here like this. And here the nonlinearity f of e is equal to e square e dot here. Here I would have u, and here I would have mu over s square minus mu s plus 1, and I would close loop. Okay? So this single differential equation, and here in the output I have my x. That single van der Pol differential equation, I can actually show it with this block diagram, and I will give 0 input to this system, and it's going to work with initial conditions again, and I would have x in its output. Now I can actually use this block diagram to apply the so-called describing function analysis. So we have separated the linear parts and the nonlinear parts of the van der Pol oscillator. You see there in that system. The nonlinear part here is concentrated in that function, and the linear part is concentrated in the second block, in the forward path. All right? Now, what are we going to do? So we still have a nonlinear system, and we really do not know how to analyze this. We only know the analysis. Suppose that we only know the analysis of linear systems. Okay? So if this nonlinear part, if I can approximate it with a linear system, then I can replace this nonlinear block with its linear counterpart, and then I can use linear control theory tools here in order to continue with the analysis. Okay? So that is what describing function analysis does. Describing function analysis replaces this nonlinear component with one type of linearization of this nonlinear component. Okay? And that linearization, or the linear block that we are going to replace this nonlinearity with, is going to be called the describing function of this nonlinearity. Okay? So we will replace this nonlinear element with its linearized version, which we are going to call the describing function, and then we are going to continue our analysis using the linear control tools. So how should we replace this nonlinearity with its linearized counterpart? The earlier linearization that we have learned so far is not really useful here, okay? Because we know that these signals are not going to be constants, okay? So linearizing this function around a constant will not be useful, okay? Because this E, we are after the oscillations here. What is going to happen to oscillation? And this E is going to change with some magnitude, and the usual linearization might be useless with that large operating range. Okay? So here, describing function analysis makes this linearization in frequency domain. Okay? So in time domain, I know that the signal E is going to cover cover a very large range if it is oscillating. Okay? It's not going to remain in a small neighborhood of some value. In time domain, E of t is going to oscillate, and it's going to cover a large range of values. That means that the linearization in time domain might not be really the solution here. But in frequency domain, I know that an oscillation would really cover a very small frequency range. Okay? if I have an oscillation with some frequency, then in frequency domain, the frequency coverage of an oscillation might be really small. That is why describing function analysis makes the linearization in frequency domain. Okay? That is what we are going to do here. So here the microphone battery is running out, so I need to change it. So I will stop this, but it's going to be instantaneous for you. Okay, now I changed the battery, sorry for this. So here let us see how we're going to replace this nonlinear block with this linearized version. So in order to be able to work with oscillations, here is what I'm going to do. This signal is E of t, the error signal. I will assume that this signal has a pure sinusoidal oscillation. Okay? I will assume that E of t is E hat times sine omega t, a pure sinusoidal oscillation. And then I will look at U of t. Okay? So let me write E of t is equal to E hat sine omega t. E hat is the amplitude of the oscillation, and omega is the frequency of the oscillation in radians per second. All right? Now I will calculate U of t here, which is going to be U of t. We know that it is f of E, but it is E square times E dot. Okay? Let us take E square, E hat square, sine square omega t, and E dot is E hat times omega times cosine omega t. Okay? So now let me collect all of the like terms together. E hat cube, I have omega, sine square omega t, cosine omega t. So you see that this is a quite complicated term, but you see that it is still periodic with the frequency omega. Okay? This term is still periodic with frequency omega. So I can expand any periodic signal with frequency omega into a Fourier series representation. Okay? So I can actually expand this as the sum of sine omega t, sine 2 omega t, sine 3 omega t, etc. So I can expand this term into sine and cosine omega t and their higher harmonics. Okay? That is what I would like to do here. I would like to expand this into its Fourier series expansion, and what I'm going to do later is that I'm going to neglect all of the higher order the harmonics here. So that is how linearization in frequency domain would be done. So here I can use Fourier series expansion formulas here, and that is what we're going to do in the later parts of this course. But here I'm not going to do it, and I'm going to try to expand this into its Fourier series expansion using some analytical trigonometric manipulations. So the first thing that I'm going to do is that I can know that the sine square omega t is nothing but 1 minus cosine 2 omega t over 2. Okay? I can replace sine square omega t with this. Okay? That is going to give me E hat cube omega, and I would have 1 minus cosine 2 omega t divided by 2, and I have cosine omega t still. I can take 2 outside, E hat cube omega over 2, and I would have cosine omega t minus cosine omega t cosine 2 omega t. Okay? So this term is fine. This is one of the terms of the Fourier series expansion. That is good. But I don't like these terms still. And in order to be able to get rid of this, I will use another trigonometric approach. So cosine A, cosine B, I know that this is 1 over 2 cosine A plus B plus cosine A minus B. Okay? So I can actually use this formula to replace this cosine multiplication with the cosine summation. All right? So that is E hat cube omega over 2. So cosine omega t here, and instead of this I will write minus 1 over 2 cosine sum, cosine 3 omega t, and cosine difference, minus 1 over 2 cosine. Difference is minus omega t, but minus would not matter in cosine, so I would just write this. Okay. So that is going to be equal to u of t is equal to e hat cube omega over 2. I would have 1 over 2 cosine omega t here, so I would make this 4 cosine omega t, and minus e hat cube omega over 4 again, and cosine 3 omega t. So you see that this is like a Fourier series expansion of this periodic signal, okay? It have cosine omega t, cosine, the coefficient of cosine 2 omega t is 0, coefficient of cosine 3 omega t is minus this thing, etc. Okay? And if I forget about this nonlinearity, suppose that you give a system this input, E hat sine omega t, and suppose that you get this output from that system. Suppose that you have a black box, and into that black box you give this input and you get this output. Okay? Now by looking at this output, can you say if that black box system is linear or nonlinear? By just looking at that input and the output, can you say if that black box system is linear or nonlinear? So by just looking at this input and output, you need to be able to say, with the knowledge that you have in terms of system theory, that black box is actually a nonlinear system. Why is that? Because I'm supplying that system a pure sinusoid, okay? And if at the steady state I see this output, that means that when I give the system an input at a single frequency, the system gives me output components at other frequencies as well. Okay? A linear system, if you give to a linear system an input of a single frequency, then the output at the steady state can only be containing the signals with the same frequency. You cannot get it in a linear system additional frequencies like this. You cannot get higher order harmonics like this from a linear system. Okay? That means that by looking at just that input and output, I can actually say that this nonlinear block, this block is actually containing nonlinear elements because of this extra frequency output component here. So now when I go back to my system here, remember that we were assuming this G of S, this linear system, to be low pass. Okay? What does it mean? It attenuates high frequencies with larger amounts. Okay? So this U of T signal here, it is containing a component at cosine omega t, and it's also containing another component at 3 times with 3 times larger frequency. Okay? So that means that this U of t, when it passes through this linear system, which is actually having a low pass characteristics, how do I know? Substitute S equals to 0. So the gain of this system at 0 frequency is mu. Substitute S equals to infinity, it's going to go to 0. So this is going to attenuate higher frequencies. Okay? So this is a low pass type of system, and it's going to attenuate higher frequencies much to the larger extent than low frequencies. Okay? So I see that into this, when this U of t enters and passes through this linear system, these higher frequencies will be attenuated to a much larger extent. Okay? And then this signal is going to go through the loop, and it's going to come back here again. Similar things will happen. Cosine 9 omega t's are going to come. And here again there will be an attenuation of the higher frequencies. So while these signals are turning in this loop over and over, this low-pass system is going to attenuate these higher frequencies to a much larger extent than it attenuates this low frequency value. Okay? So here, because of the low-pass characteristics of this system, we are going to neglect here these higher order harmonics. Okay? That is the property of describing function analysis. We will always expand the output of the nonlinearity into a Fourier series expansion, and then we will neglect higher order harmonics. All right? So then I get the result, u of t is approximately e hat cube omega over 4 cosine omega t. Okay? So now I can actually think about how to replace this nonlinearity with a linear element. Okay? So suppose that I give you a black box with the input e of t is equal to e hat sine omega t, and suppose that the output is u of t is equal to e hat cube omega over 4 cosine omega t. What would be the linear system that you need to put here to convert this signal into this signal? Okay? That is the question that I need to answer. Our answer here, we are going to call the answer as the describing function of this nonlinearity. And then we are going to replace this nonlinearity with this describing function, and we will obtain a linear system at the end. Okay? But first we need to answer which linear system converts this input into this output. Can this be a linear system? Yes, because I have a single frequency here, input frequency, and that single input frequency appears in the output. There are no extra different frequencies here. We neglected them. So this can be a linear system now. So let me start with an easier example. Suppose that I give the system sine omega t. Suppose that the system gives me at the steady state cosine omega t. Okay? Then what is the linear system that I need to put here? I give sine omega t, and then I get cosine omega t from the output. Which linear system converts sine omega t into cosine omega t? So you might think that if I take the derivative of sine omega t, it's going to give me, so if I write d over dt, then sine omega t is going to turn into omega cosine omega t. Okay? So if I divide the result with omega, then d over dt sine times 1 over omega is going to convert sine omega t to cosine omega t. Okay? So that is pretty nice actually. So I will take the derivative of the input, and then I will divide it by its frequency, and I would get cosine omega t. All right? So what is this system in frequency domain? This is what that system is in time domain. What is this system in frequency domain? I know that d over dt is s, and I would have 1 over omega. Okay? This is the system in Laplace domain. What is this system in frequency domain then? S is j omega in Laplace domain, divided by omega, is just going to be j. Okay? So this signal, this system, this missing system, which converts sine omega t to cosine omega t, is just given by j in frequency domain. Okay? So it's just a 90 degrees phase shift. That is what this means. All right? So now let us try to apply this theory to this system. In order to be able to convert sine omega t into cosine omega t, I need a j, okay? And I also have an amplitude change here. Amplitude changes from e hat to e hat cube omega over 4. So what should I add here? If I add the amplitude change e hat square omega over 4, then I would get my system, okay? So this is the equivalent or linearized version of this nonlinearity in frequency domain, okay? Actually, this is what we call as the describing function of this nonlinearity, okay? We show the describing function with the following letter and e hat omega. It is in general dependent on the amplitude and the frequency, and in this case we have this. E hat square over 4 j omega, okay? This is the describing function of f of e, the nonlinearity. It is the frequency linearized version of the nonlinearity, okay? So then what I'm going to do now is I will replace this nonlinearity with this describing function, okay? Let me do that replacement. So I have r equals to 0, and instead of this I would substitute this thing. E hat square over 4, j omega is just s in Laplace domain, and I will just place this linear system as it is, mu over s square minus mu s plus 1, and that's all. This is the equivalent system when we replace the nonlinearity with its describing function, with its frequency linearized version, okay? So now I can actually get rid of this. So now you see that in the describing function there is an s. Now I can actually equivalently take this s into the linear system as well. Then I would get the following system. So I have here mu s divided by s square minus mu s plus 1, closed loop with unity feedback, and here I have just kind of gain here, an amplitude dependent gain, e hat square over 2. I will call this gain as capital K, and I would have this linear system here. So from this point on, what should we do? Now we have, you see, a linear system. Sometimes we can call this a quasi-linear system because parameters would depend on the amplitude and the frequency of the oscillations that we are searching for, okay? So what did we want at the end of this analysis? We want E of t to have a pure oscillation. We want E of t to have pure oscillation in the sinusoidal form, E hat sine omega t, an oscillation which doesn't grow or doesn't decay, okay? This is called sustained oscillations in control. Now we have a linear system, and from this linear system, we want sustained oscillations. We want this linear system to display sustained oscillations, which means some oscillations which do not grow, which do not decay with constant amplitude, okay? So if you consider Laplace domain, what do we need? So sustained oscillations in Laplace domain would mean something about closed loop poles of a cislinear system, okay? So remember, if you have a linear system in this form, G of S, H of S, which is what we have here. We have now a completely linear system, and the closed loop transfer function of this linear system would be g of s over 1 plus g of s h of s. And the poles, closed loop poles of this system would be determined by this characteristic equation. The characteristic equation of the system would be 1 over 1 plus g of s h of s is equal to 0. Okay? And the roots of this equation are the closed loop poles. So if we want the system to display sustained oscillations, what type of criterion should be satisfied by the closed loop poles? Can the closed loop poles be real? If the closed loop poles are real, that means that we don't have any oscillations. Everything is either decaying or growing. Okay? So we cannot have real closed loop poles. So we want complex conjugate closed loop poles. If I have complex conjugate closed loop poles like this, so suppose that their real part is -3, I made this up. In that case, do you see closed loop, do you see sustained oscillations in the system? Remember that real part of closed loop poles would determine the decay or the growth rate of the oscillations. So if I have closed loop poles like this, then that means that in the response of this system, I would see e to the minus 3t cosine omega t and e to the minus 3t sine omega t like terms. So the frequency is determined by the imaginary part of the closed loop poles, and decay rate or the growth rate, this is determined by the real part. If the poles are in the open left half plane, then the oscillations would be decaying. If I have closed loop poles here in the open left half plane, the oscillations would be decaying in the system. What would happen if I have the reverse scenario? If the oscillations, if the closed loop poles are here and here, with the real part +3. In that case, I would see e to the 3 cosine omega t, e to the 3t sine omega t in my response. Okay? But these are oscillations which would be growing indefinitely. We would have an unstable closed loop system in that case. Okay? So the real part always appears here into this exponential. So then, what conditions should we have in order to be able to get sustained oscillations from this linear system? The answer is simple. We cannot have complex poles on the right half plane. We cannot have complex poles in the left half plane. We need to have complex conjugate poles exactly on the imaginary axis. Okay? For the linear system to have sustained oscillations. And what will that mean? We are going to have e to the 0t cosine omega t, e to the 0t sine omega t, but you will see that this e of 0t is e to the 0, which is 1, neither grows nor decays. Okay? So we have sustained oscillations in that case. So what we want from this linear system is to have closed loop poles exactly on the imaginary axis for sustained oscillations. For having this type of error signal whose amplitude is neither decaying nor growing, we need to have closed loop poles exactly on the imaginary axis. Okay? Let us write that condition. 1 plus, GH is everything in the loop, open loop transfer function, K times mu s, s square minus mu s plus 1 is equal to 0. Then let us find the characteristic polynomial, s square minus mu s plus 1 plus k mu s is equal to 0. And then this is s square plus mu s in mu s parentheses. I would have k minus 1s plus 1 is equal to 0. And I want sustained oscillations, meaning that I need to substitute s equals to plus or minus j omega here. I will substitute plus j omega here. And that is going to give me minus omega square plus mu k minus 1 j omega plus 1 is equal to 0. And I want this to be completely equal to 0, so the real part should be equal to 0 and imaginary part should be equal to 0. 1 minus omega square plus mu k minus 1 j omega is equal to 0. And if the real part is equal to 0, I have omega square is equal to 1. And if the imaginary part is equal to 0, I would have mu times k minus 1 omega is equal to 0. So mu is not equal to, mu is strictly positive. So that means that I have three possibilities here. Either k is equal to 1 or omega is equal to 0. And here I have omega is equal to plus minus 1. Okay? Can I have omega equals to 0? So here we are looking for oscillations. So we want non-zero omega here. Okay? Zero, an oscillation with zero frequency is not really an oscillation. Okay? So really, I really do not care about this omega equals to 0. So these are going to be my answers. K needs to be equal to 1. And omega has to be either plus 1 or minus 1. And I see here k equals to 1, but k was equal to e hat square over 2. Sorry, this is e hat square over 4. There's a mistake there. Sorry for this. This e hat square over 4 was k, and that needs to be equal to 1. Okay? That means that e hat square is equal to 4, meaning that e hat has to be plus minus 2. So we have found the amplitude conditions. E hat is either plus 2 or minus 2, and the frequency has to be plus minus 1. This is radians per second. Okay? So now let us look at this frequency. If I would like to find the period of oscillations, I need to, let me take one of these. Omega equals to 1, then this is 2 pi over the period. And that is going to tell me that the period is 2 pi seconds. Okay? So that means that I would have 6.28 approximately seconds of period, an oscillation period. Okay? So this is what describing function analysis would look like on this type of system. What did we do here? We first converted our differential equation into a standard form that is useful for feedback for describing function analysis, and then we replaced our nonlinearity with a form of its linearization in frequency domain, which is called describing function. And then we obtained a linear system at the end, and we enforced that system such that it has closed loop poles on the imaginary axis. And the imaginary part of that closed loop poles would be the frequency of oscillations. We have identified it either as plus 1 or minus 1. And we have also found the possible amplitude values that we can have here. So we have found these values, but we really do not know whether they are actually valid or not. So we are going to actually try to see whether these values are valid or not in a computer simulation. I will try to illustrate this system, the response of this system in MATLAB actually, and I will try to do it in the next lecture of this course. That's all for this one. See you in the next lecture. Bye.